All right, mean value theorem. If f is a function that satisfies these conditions, and these have to be true for this work, that it's continuous on a closed interval, things we've heard before. It also needs to be differentiable on that interval. Then there is at least one number c in the interval from a to b such that this statement is true, and this is mean value theorem. And what this is looking at here is this is your average rate of change. And you've seen this formula before. Mostly you've seen it written more like this. So y2 minus y1 over x2 minus x1. It's just slope formula. So if you want to find the slope between 2 points, that's going to give it to you. That's why that's average rate of change between A and B. This side is a derivative, and we know derivatives also find rate of change, but what a derivative finds is the instantaneous rate of change at a point. So in essence, it's saying your instantaneous rate of change equals your average rate of change at least 1 point. So what does that look like picture-wise here? What it means is if you have 2 points here between A and B here, so if you follow that up, there's y values for both. The average rate of change would just be this line. That's your f of b minus f of a over b minus a. That's that part of mean value theorem. On the graph of that function then between those 2 points, somewhere along there is at least 1 point where the tangent line right here has the exact same slope as your average rate of change. So the tangent slope is parallel to the average slope at least 1 point. It might be more than 1 point. This graph over here shows that on this one, there's two values that give that. So there may be more than one, but you're guaranteed at least 1 point if it's closed, continuous, and differentiable. Let's try one out. Show that this function satisfies the mean value theorem on the interval from 4 to 9. So first off, is this closed? Yes, it's closed. So we want to. It's a closed function. We can see that. You can see that over here. Is it continuous? Well, we got to be careful with natural log. There are certain values where natural log doesn't work. But if we're going from 4 to 9, any number we plug in between 4 and 9 here keeps the number that we're taking the log of bigger than at least 1 here. And so we can do logs of any positive value. So it is continuous. And finally, is it differentiable? Everywhere here. Well, let's see what that derivative is and find out, because if we know the derivative, we can get that. Our derivative here, y prime, would be 1 over whatever we're taking the log of. And we got to do chain rule here, times the derivative of the inside would be 1. So that's our derivative. Looks like the only place where that derivative doesn't exist is at 3. We're okay here, though, because we don't pass through 3 on our interval. So yes, we've checked off all 3 of these. They satisfy the different qualifications of mean value theorem. So now let's actually apply mean value theorem to this then and find out what we get. So to apply mean value theorem, we want to set that derivative equal to the average change here. So we found our derivative already. Our derivative was 1 over x minus 3 in this case. So if we want to have c as our thing, that's fine. We'll just change this to a c. On the other side, what is f of b, f of a, and b minus a? Well, our 2 points again were 4 and 9. So those are our x values. Our y values on top are what we get if we plug those numbers in. So if we were to plug in 9 up here, 9 minus 3 is 6. So this is going to be natural log of 6. minus if we put 4 in that same spot. 4 minus 3 is 1. Natural log of 1 ends up being 0. And so that's what we come up with now. So now it's just trying to simplify and solve this out and seeing what we get when we do that. So next, what we can do here is this would just be natural log of 6 over 5. Over here we got still our 1 minus c minus 1 over c minus 3. Let's cross multiply now and see what we get here. So if we cross multiply, we got just 5 on the one side. The other side we got natural log of 6 times c minus 3. To solve for that, we could either distribute or let's just divide to get rid of that natural log 6. So now we got c minus 3 equals 5 over natural log 6, and then finally add 3. So the exact value where this is going to work here is that 5 over the natural log of 6 plus 3. That would be the exact location where the average slope is parallel to the tangent slope. Just to check, that should be a value between 4 and 9. You could jump on a calculator and just see what that approximate one comes out to be. So if we do 5 divided by natural log 6, and then add 3 to that, that should be a number between 4 and 9 somewhere, and yes, it is. It's about 5.791. Okay, another application of this one. Suppose a car drives 200 miles in 3 hours. According to mean value theorem, do we know these things are true? At some point, was the car traveling 60 miles per at least 60 miles per hour? So this would be like our instantaneous rate of change. Can we compare that to our average one? Well, can we figure out our average rate of change here if this person drove 200 miles in 3 hours? Yeah, we should be able to. If we just divide that, that would give us our average rate of change. So if we go through and divide that out, what that tells us is our average change is 66.6 repeating miles per hour. All right, so would we have to, if that's our average, would we have gone 60? Yes, so we can say for sure, we know at some point here we must have gone 60 miles per hour if the average ends up being 66.6. So yeah, so we can confidently say that this car did go 60 at some point. Did the car go at least 65 at some point? Yeah, I mean, again, if our average is 66, we must have gone 65 to get to an average of 66 at least once, because this car must have gone at least 66.6 repeating miles per hour at some point. Was the car traveling at 70? Well, here we get into some unknown here. Answer to this one, we can't say conclusively yes or no. Possibly, maybe, it went 70. It could have had this average rate of change, though, without going that high. So we can't definitely say it went 70, but it could have. But mean value theorem can't prove that. The most we know is that it did travel 66.6 at some point. All right, one last problem here looking at mean value theorem. Suppose that f of 0 is equal to -3, derivatives less than 5 for all values of x. How large can f of 2 possibly be? If you see problems where they talk about slope end points, good chance this is still a mean value theorem question. So let's write out mean value theorem again. It's that derivative at c equals fb minus f of a over b minus a. So what do we know? What do we know here? Well, we have we have some points we're talking about here. F of 0, F of 2. So let's use those as our 2 points here. 2 and 0, and that means this will end up being F of 2 and F of 0. Over on the left side, we have a derivative. Do we know a derivative here? Yeah, we know the derivative's always less than 5. So rather than having an equals on this one, let's just say we know this then is always, our derivative is always going to be less than 5. That means whatever this is equal to should always be less than or equal to 5. All right. Next, now, what we want to do is try to fill in what we know here. So, is there anything here that we know? The one thing we do know, f of 0 equals -3. So let's plug in that information. And then if we solve this, we should be able to say how large f can possibly be here. So minus a negative, we can turn that into a +3. Also here, it's being divided by 2. Let's times both sides by 2 here. I'll get rid of that. So now we know that this is less than 10. And if we minus 3 here, that's going to tell us that f of 2 has to be something less than or equal to 7. So how large can f of 2 possibly be? It looks like the largest it can end up being is 7. 7 would be the biggest possible value for f of 2. It has to be something less than that for that slope to end up being less than or equal to 5. So that's kind of another twist on the mean value theorem that they've had problems that have shown up that look like that before.